or if you are all hearing me clearly. Is everyone hearing me clearly? I need someone to confirm if you can hear me clearly. Can somebody confirm that? Can you hear me clearly? I need someone to confirm if you can hear me clearly. You can talk so that I'll be able to know if you are hearing me clearly. Is everyone hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. I want to welcome you to another statistical learning class. Of course, I'm having a remote class today because of the little emergency that I got. So we're starting a new topic that we call support vector machines. We've been working on classifiers, before now we work on how do we, solve a prediction problem and how do we solve classification problem. Okay, so I remember I've walked through the KNN classifier, the CN, the Bayes classifiers. We've gone all the way, to do what I call the linear discriminant analysis. We've talked about quadratic discriminant analysis. You know, we've worked on different kind of, stuff. So, today we want to focus on support of vector machine. And of course, last time I walked you through regression trees, or we did bagging, we talked about random forest and so on like that. Find ourselves in the world where we got different techniques that can be used on the same purpose. It is now left to us to identify the one that is deemed more appropriate, for our situation. So I want to welcome you to support vector machine. And of course, from today, when I say support vector machines, okay, we actually be focusing on three type of classifiers. Okay, the one I call the Maximan margin classifier, the support vector classifier, and the support vector machine. And let me tell you this, um, one is going to be a generalization of the other one. So I'm going to start from the a special case before moving into the general case. Okay, so let me tell you this. We want to focus on classification here, and to be able to classify, we normally identify a kind of a threshold, but here we're going to be making use of what I call an hyperplane. So the hyperplane is what we're going to use in performing the classification. So because we're going to be using hyperplane for that, so I think I'm going to walk you through, what we mean by that. Okay, so we believe the hyperplane that we're focusing on will be in a p dimension. Okay, so when it is in a p dimension, okay, we actually gonna be referring to that as an hyperplane in p dimension is a flat subspace of dimension p minus one. So what do I mean by that? What I mean by that, okay, the two dimension, the one I call 2D, okay, is going to correspond to a line, and the three dimension will be called a plane. I'm going to say that again. For two dimension, we're going to use a line for two dimension. We're going to use a plane for three dimensions. Now, I need you to pay attention to what you're seeing right now. I'm showcasing a three dimension X, Y, Y, and Z, and I have some kind of data points that have been classified. Okay, you can see the one in X, you can see the triangular one. Okay, so that is going to be the job. But the main thing is, can we have a mathematical way, to figure this out where we need to identify, the hyperplane that will separate, the data, the observations. So in mathematical term, okay, we're going to write an equation, okay, that will represent the p-dimensional hyperplane. Okay, do you remember what we done before? This is looking like a systematic part of a model. That's a linear combination. So we're going to say, okay, that guy equal to 0. Okay. Now, when you take a look at the dot here, can you see the dot right now? Okay, the one here. Okay, the one that is look at this line here, this particular one here. Okay. Now, we actually going to say, okay, that is where all of this equal to 0. So which means something below that, something above that, will be the region of classification. So, and I need you to pay attention now. Now, if you take a look at this, I got greater than 0, right? Now, that will be the axis. You can see the axis now. Okay, greater than 0, because since you have identified this to be 0, okay, then anything above that is going to be greater than 0. And anything below that is going to be less than 0. That's what you see here. So the one, the triangle, okay, can you see that? And that is actually, so because when you set a threshold, we're going to consider below the threshold and above the threshold. That's what I mean. And that is exactly what we're talking about here. Okay. And I need you to pay attention to that. That's what I talk about. You can see greater than 0, you can see less than 0. And, all of these, they're actually giving us information. Okay. So this is talking about hyperplane. Let me tell you the hyperplane, what the hyperplane does is to maximize the distance, okay, between the two closest points in the two classes. Okay, is there a way I can maximize the distance between this guy and this guy? Okay, they are so close. They are in different classes, but they are kind of close. You get what I mean? They are kind of close. Okay, is there a way we can maximize the distance? Okay, so we're going to talk about as time goes on. I'm going to tell you the kind of distance. Is it going to be Euclidean, or is it going to be perpendicular? Okay, I'm going to tell you the one, but let me just tell you this. The idea here, can we have a way, to maximize the distance between the upper plane and the nearest data point? The nearest data point, okay, without us allowing any kind of misclassification. So I need you to pay attention. So, uh, you know, you can see our f of s, okay, the 1, 2, and 3, the one that is equal to 0, greater than 0, less than 0, they're telling us story, okay? They're just telling us, the side where the x lies, okay? The side where the s lies, the moment I know equation 1, then it is 0, 1. Above that, below that. That's what I mean. Okay, so it's like it's dividing the p-dimensional polynomial into two halves. That's what we have. Okay, it's dividing that into two halves. Okay, now, so that is the explanation for that. But you know what? We normally start with a data matrix X, where you're going to have, the row will be the observation, the column will be the numbers of features. Okay, and of course, we actually going to call that n observations in p-dimensional space. The dimensional space here is actually going to be determined by the numbers of features. the numbers of Pleiadios. Okay. And you know, the other time I said here, greater than zero, less than zero, the smallest number we can think of when it's greater than zero. Okay, let's talk about one. When it is less than zero, excuse me, let's talk about negative one. And that's why you see here, okay, the way we actually going to assign the observation. So we're going to believe the observation is going to fall. Okay, so that fall into a class y equal to negative one or y equal to one. So where is the one and negative one coming from? When it's greater than zero, the smallest number that is greater, I can consider one. When less than zero, I can consider negative one. So that's what I mean. Now, because when you look at the nature of y itself, don't forget you're doing classification. So we believe the response variable is categorical. So it's going to have a label, okay, in the real data, in the original data. Okay, it's labeled as 0, 1, right? It's labeled as 0, 1. If I want to classify new observation now, okay, if I want to classify new observation now, I'm actually going to use 2y minus 1. Okay, and I'm going to show you how it's going to work. When you plug in 0 for y, that's going to be negative 1, right? When you plug in 1 for y, 2 times 1 is 2, 2 minus 1 is 1. Can you see that? Okay, so that is kind of classifying new observation. Okay, I'm classifying the new observation. So the classification rule now is actually, when y is negative 1, it's going to be in that class, and for 1, it's going to be in the other class. So take a look at that. Okay, now I'm going to move. Okay, now, you know, if you want to classify, you could have vectors of features. Okay. Oh, new features that I want to I want to classify. I remember I used some example in class the other time, when I was walking you through random forest bagging and decision and regression trees, where I use an example from, customers approaching a bank for loan. Okay, it's either the customer is going to be or giving the loan or not. And of course, before they're going to take a decision, they're actually going to consider, some features. Okay, so let's say customers with these new features now came into the bank, approached the bank for a loan. The features like credit history, the balance on the accounts, your income and so on like that. Okay, that's what I mean. So these are new observations. These are not part of the original, that I said. Okay, or probably these new individuals, they are not new to the bank, but except that they are still customers in the bank, but they've not applied for loan in the bank before. Okay, and the model the bank is going to use for that, this is going to force, discriminate you with the convention, with the original data set that have label. Okay, so this one doesn't have label because we don't know whether they're going to default or not. But can we actually use this approach here, you know, to classify them into whether they're going to default or not? Okay, based on their history, the credit history, the income and so on like that. So, and that was why I said we want to predict the class, the observation belong. Are you going to default or not? And if you want to do that, okay, now you remember what I said about greater than, the linear, the function is going to be greater than zero, going to be less than zero, greater than zero, we consider one, less than zero, we consider negative one. Okay. And of course, I'm going to show you the pictorial, take a look at that now. Okay. Can you see that now? So, this is a situation whereby we have you know um uh two features, okay, and probably we want to the dates. Okay, we want to assign observation with that into class. That's what you see here. So you can see the kind of hyperplane, I just mentioned. Okay, so take a look at that. Okay, so and I asked a question. I said, how will you assign a class to the test observation? Okay, and of course, we actually gonna have a rule to do that. Okay, so if we have a new observation which lie below the upper plane, so which means you need to four of us identify the upper plane. Okay, we're gonna identify hyperplane that's marginally, that separates, the two classes based on the training data. Okay, and we're just going to be looking for the position, the new observation is going to for, like I said here, if we have a new observation which lie below the upper plane. Okay, S star equal to that. For this time we have a S star, equal to that. We'll take a look at the S star equal to that. Don't forget we consider X1 and S2, right? Okay, considering S1 and S2, then we say we're going to assign that to class -1. That is for y equal to -1. Okay, and if we have a new observation which lies above the upper plane, okay, then we assign that to class 1. Okay, so that is going to be the rule. But the question is, if I find the magnitude of the linear combination, okay, that involve the new observation S star, what does it tell us? I need you to pay attention. You don't understand. Make sure you ask question. Okay. I want to do something right now. Okay. I have my model and I've plugged in the new observations. You can see S star, Y S1 star up to that. And I take the absolute value of that. What kind of information is it telling us? The information instead is going to be telling us is it's going to tell us the amount of confidence we have in the classification. And that's what I'm trying to say here. I said, the magnitude of this guy will tell us how confident we are in assigning, members into class -1 or 1. Okay, don't forget you're assigning new members. Like I said, those who are new, they are not new customers in the bank. They are actually, um, you know, they are existing customer, but except that they've not applied for loan before, and that is going to make them to be new observations, like I said. Okay, so take a look at that. Okay, now because of this, you know what I want to do? We have three type of classifier. Okay, we have what we call the Maximan margin classifier. We have this, support vector classifier. Okay, and we also have support vector machines. But I'm going to spare my time, okay, explaining the first one that I call the maximum margin classifier. Okay, what do we call the maximum margin? Why is it called the maximum margin classifier? Before moving on, can somebody confirm again if you are still hearing me clearly? Is everyone still hearing me clearly? I need a confirmation. Is everyone still hearing me clearly? Okay, thank you for confirming that. If you are not hearing me clearly, please let me know. Now, what do I mean by maximum margin classifier? I'm going to say this is a linear classifier, okay, that actually found the upper plane with the maximum margin, okay? When I say upper plane with the maximum margin, I'm trying to say the farthest possible distance from the closest data point of any class. Now, I needed to see this. You see the X, you see the circles one, right? I needed to pay attention, take a look at the two. Okay, take a look at this, take a look at that. Okay, now we are actually, if you take a look at this one now, this is the one that is closer to the one here. We want to maximize the distance between them. I'm going to say that again. We want to maximize the distance between the two closest points in the two classes. Okay, so and that is the reason why the maximum margin classifier can be called an hard classifier, because the assumption here is that it works when data is perfectly linearly separable. We don't want to tolerate any misclassification here at all. No misclassification here at all. Okay, and you know what? We're actually going to use the distance that we're going to use between the two closest points in the two classes. The distance is going to be perpendicular distance, because the perpendicular distance is going to be robust. It's more robust and more generalizable than Euclidean distance. So we are not going to use Euclidean distance. We're going to use the perpendicular distance. So the maximum margin classifier, okay, like I said, it has the assumptions, that the data is perfectly linearly separable. Perfectly linearly separable. We do not want to tolerate any misclassification, and that is why this is called hard classifier. Okay, hard. Okay, HARD classifier. It's not a soft. So soft at all. So it maximizes the distance between the upper plane and the nearest data point. Okay, the nearest data point, okay, that I call support vector, without us allowing for any classification. Okay, but let me tell you the issue with the maximum margin classifier. It's not realistic. I'm going to say that again. It's not realistic. If you know, it's not sensitive to outliers, and not even realistic for most of real world data. Okay, this particular classifier that I just talked about. Okay, so I'm gonna show you some stuff. Please pay attention. Okay, pay attention. Now I'm gonna show you the hyperplane that I talk about. Okay, here now, the hyperplane is this solid line. Can you see this solid black line? That is the hyperplane that I just talked about. Okay, now let's look at 2 points that are very close, and they are in different classes. Oh my God. Look at the one, this guy on this black dotted line. Can you see that one? And look at this one, the reds, this one here. Okay, if you take a look at that. So we want to look at we want to maximize the distance between the upper plane and, you know, the two closest point from both sides. Okay, so the one on the line, on the margin, okay, we call them support vectors. This guy is a support vector. Okay, the one on the margin, okay, they are called support vector, the one on the margin. Okay, and here, if you look at what I'm seeking a perpendicular distance, okay, between the upper plane, okay, the and the margin. So we are not going to use Euclidean distance, because Euclidean distance is not robust, it's not generalizable. Okay, so I just wanted to see that. And of course, and we're never going to tolerate um what I call misclassification at all. So this is the upper plane. Okay, now is there any question on this picture? Is there any question on this picture? So like I said, we seek to maximize. Let me give you an example of this in real life. I need you to pay attention. Okay, when can we use a maximum margin classifier? Don't forget, I said this particular classifier, okay, has an assumption. It only work when the data is perfectly linearly separable. The example I'm going to give for this in real life is when you want to distinguish, okay, you actually want to distinguish between men's and women's shoe size in a specific region. I'm going to use United States markets. Okay, I want to distinguish between men's shoes and women's shoe size. Okay, of course, the feature is going to be that we're considering is shoe size. Okay, and of course, the class label is male and female, right? We actually want to be able to allocate, shoes, classify shoes as the male shoes and, based on the feature, based on shoe size. Okay. And let me tell you this, what is going to be the boundary? A clear boundary for United States market is size 7. I'm going to say that again. Size 7. I'm talking about United States. Okay. Size 7. Okay. Size 7. I'm talking about shoe size. Okay. I'm talking about shoe size. Okay. I actually want to talk about the real life application of this classifier. Okay. Maximum margin classifier. Okay. So we can actually find the hyperplane, which is the threshold that will separate both classes perfectly with a maximum margin and no misclassification at all. Okay, no misclassification at all. And let me tell you this, because the data is linearly separable, we don't need to tolerate any mistakes. When I say we don't need to tolerate any mistakes, it means we are not giving chance for misclassification. That that's exactly what I mean. So the perpendicular distance, don't forget, we said it's going to form a 90. Can you see 90 degree? Can you see right angle, right? 90. Okay, that's a 90 degree. So pay attention to that. Like I said, we're using perpendicular distance and not, you know, the Euclidean distance. So the perpendicular distance between the point, when I say the point now, the closest point, okay, that's what I mean. The closest point at both sides of the aisle. We want to maximize the distance. That's exactly what I mean. Okay, now, but let me tell you this. We could have possibility of having over fitness. Okay, I know I said something here. So the underlying assumption is that if the margin in the training set is large, okay, if the margin, so what I mean by margin, okay, the dotted line is a margin. Okay, the dotted line is a margin. How do I get a dotted line? That is where the closest, okay, the closest points in a particular class. Okay, there's a margin here too. Okay, okay, so that is the closest to the upper plane. Okay, that's what I mean by margin. So what I'm trying to talk about is, I said if the margin in the training set is large, then the margin in the test set will also be large. Okay, and of course, for large features, that the approach may lead to overfitting. Okay, overfitting is having high variance. We are it's going to perform great. The model perform great on training data, and of course, it's going to perform poorly on the unseen data. Okay, now I'm actually going to move into where I'm still on maximum margin classifier. Right now, I'm actually going to walk you through the mathematical aspect, the optimization aspect. Okay, I'm actually going to show you that since we are maximizing distance, of course, we're going to get into maximization problem. Okay, so I said the training observations which lie on the margin, okay, we call them support vectors. Okay, this is what I'm talking about. This point here, it's on the margin. Can you see that point? Can you see this point? Okay, they actually call support vectors. Okay, now, and I said, what is going to happen? Please pay attention. If I actually change the position of the support vector, okay, what is going to happen? So the margin and the upper plane will change. So this is what determine. What determine is the closest point. Okay, the closest data point of any class is what is going to be the determinant. So changing that, changing their position, okay, it's also going to change the hyperplane. That's what I mean. So it's going to change the hyperplane. But what if we change the position of other observations, which is not a support vector, like all of these ones, all of these ones, okay? Okay, let me do this. The one that are not support vectors, okay, that are not. Although this one, they are not. And this one, they are not. They are not support vectors. The one that is a support vector is this one, this one, this one. Even this one is not. They are together, even that one is not. Okay, so the one on the margin is what we mean by support vectors. Okay, they're very, very crucial. Pay attention. They're very crucial. Okay, now I said if we change the position of observation, which is not a support vector, nothing will change. Okay, nothing will change. Okay, so it is only when we change the support vector, okay, that when you change the support vector margin, okay, so when you change the support vector, the margin and the respective hyperplane will change. So the takeaway is that what the position of the support vector affects the margin and the hyperplane. Okay, when you change the position, it's going to affect the margin and the hyperplane. The margin was a black, dash line, while the hyperplane was, the black solid line that I just show in the, the picture. Okay, now I want to take you into the mathematical aspect of that. Okay, how can we construct, the maximum margin hyperplane? I need a maximum margin hyperplane when I'm using a maximum margin classifier. Okay, now we're going to have an objective function. What do we want to do? We want to maximize the distance. Okay, I want to, the M here represent the width of the margin. Don't forget, it's a maximization problem. And if you want to do that, it's going to be subject to, subject to that equal to 1. Subject to that equal to 1. And of course, you know, that y multiplied by that greater than m. Okay, so we actually gonna tell you what is intention of 8 and 9. Okay, the essence of putting 8 is for the perpendicularity. I talk about, that okay, we're also imposing perpendicular distance. So and that was why I said, it's introduced in order for us to guarantee, in the maximization, we want to guarantee perpendicularity. Okay, we want to guarantee the perpendicular distance of the observation, whatever observation from the upper plane. So that's why we need this guy here. And of course, why do we need 9? Okay, why do we need 9? Because the 9 is the one that have a greater than m, right? Okay, we need 9, because that will guarantee the observations of the same class will be on the same side. We want an observation, of the same class to be on the same side of the hyperplane. So this is going to guarantee that. So that's what I mean. And of course, the main intention is to maximize the width of the margin. Okay, but you know what? Unfortunately, in real life, we may not have something like that, like where you're going to have a perfect classifier where there's not going to be any room for mistake. Okay, we live in a stochastic environment where that may not be happening. Okay, and that is the reason, imagine you have this kind of situation. Okay, you see the kind of situation now. This is what we are likely going to have in a real life. Take a look at that. You can see that this is kind of overlapping here. Okay, and that was why I said in this situation, we need to extend the concept of separating hyperplane in order to cover for those situations. Take a look at that now. Can you see that now? So we may not be able to have a perfectly, separating situation. Okay, so So which means we need to consider some kind of soft classifier that we allow overlapping, that we also allow misclassification, okay, and that is going to be robust, okay, and because of that, we're going to move to support vector classifier. So support vector classifier is a soft margin classifier. Okay, it's like I said, it's a soft margin classifier because it's realistic in the reward. Okay, it's going to allow some kind of misclassification. Okay, and because of the fact that it allows some kind of misclassification, it will make the model to be more flexible and robust. Okay, when our data set is not perfectly separable. Okay, but the only key parameter here, it has to do with C cost. Okay, I'm gonna write that now. So C cost. Okay, so we actually cost C, which is the cost. Okay, now don't forget we are tolerating mistakes, right? We are tolerating misclassification. Then we need to have a control. We are going to have control the trade-off between maximizing the margin and minimizing the classification error. Okay, you can see in the other one we didn't talk about misclassification error in the maximum, margin classifier. We didn't talk about classification error because we didn't tolerate any of that. But right now, since we want to make their model to be more robust, and we're actually gonna have a kind of a trade-off, or something parameter that's really gonna have as a trade-off, between, maximizing the margin and minimizing the classification error. Okay, I'm going to show you something now. And when I say the cost, we can have a high cost, we can have a low cost. Okay, now when I talk about the low cost, the low C, I mean, I'm talking about the parameter C now, okay, that I said we're gonna have. So we're gonna have a low value, we're gonna have a high value, okay. The low value of C is talking about a wider margin, okay, a wider margin, more tolerance for misclassification. But why the high C is going to be narrower margin, less tolerance. Okay, narrower margin, less tolerance. So let's take a look at this picture right here. Looking at this picture now, okay, like I said, using a soft classifier, okay, observation will belong to two different classes that cannot be perfectly separated by separating up a plane. Okay, observation which belong to two different classes that can be perfectly separated, by separating our plane. But this is not most desirable. Take a look at this. I got two observation now that I need to classify. This guy here. Okay, so which boundary am I going to use? Am I going to use the one from the maximum margin classifier? The one from the maximum margin classifier is this the black dotted line. Okay, why the one that we want to tolerate right now, okay, is actually this guy. So take a look at what I have now. That was what I said. That guy, decision boundary of the maximum margin classifier, and this guy, if we're to get this particular, so what I'm trying to say right now is that we're not going to use the dotted line, the black dotted line. We're going to use this one, okay, the solid line, okay. So we're actually going to use the blue line. That blue line would do a very, very great job, okay. Why do I say blue line? Okay, if I use this guy, you're going to see that this guy is on the same plane with this particular observation here. Take a look at that, okay. So because below that one is going to classify this as this. And let me tell you this is for the other group. Can you see that? This two is for the other group. And that is why, okay, we because of the fact that these two observations, they are kind of overlapping, okay. So using this maximum margin classifier is not going to work. And that's why we're actually relaxing that. Okay, now I need you to pay attention. This is some more than one. If you take a look at what I have here, the black solid line is the upper plane. This the dotted line is the margin. Okay, I need you to pay attention. We got some observations that are on the margin. You know, I told you the other time that the one we call the support vectors, right? Okay, now if you look at observation 1 here and sorry, observation 11 here and observation 12, they are misclassified. Please pay attention. You can see 11 is having this color, supposed to be here. 12 is having the blue color, is supposed to be here. So I said observation 11 and 12 are said to be on the wrong side of the upper plane because this is the upper plane. The solid black line is the upper plane. They are on the wrong side of the upper plane, and not only that, they are also on the wrong side of the margin. Okay, this is the margin here. Can you see the margin here? Of course, this is not on this particular margin here, and this 11 is not also on this particular margin here. So the observation 11 and 12, they are on the wrong side of the upper plane. They are also on the wrong side, okay, of the margin. Okay, but I wanted to look at observation 1 and 8. Observation 1 and 8, don't forget, observation 1 and 8, they are the closest point to the upper plane, right? I need you to pay attention now. I'm talking about observation 1, okay, and observation 8, okay? They are on the wrong side, okay? They are, and they are said to be wrong side of the margin, but they are on the right part of the upper plane. Okay, why are they on the right part of the upper plane? This is an upper plane. Take a look at the upper plane. They are on the right side of the upper plane, but they are on the wrong side of the margin. Okay, so take a look at that. So that is the interpretation that I'm actually going to give to that. And of course, we said the only observations which will be misclassified are those one which violate the upper plane. I'm not interested whether an observation, violates the margin, but the only major concern is when it violates the upper plane. So when it violates the upper plane, then it's going to be misclassified. Now, like I said, the purpose of the support vector machine is actually, to we have a way of soft classifying where we're going to tolerate, yeah, some kind of misclassification. So the real life application of this is in spam detection, email spam detection. Okay, where some emails might be borderline. Okay, when I say borderline, illegitimate email with proportional terms, or just a or illegitimate email with promotional terms. Okay, at times you're going to get some emails that they're going to say, okay, we have offered you a job, right? We have offered you a job. It may be genuine, it may not be genuine. And that was why I said, there's going to be some email at the borderline, okay? A legitimate email with promotional terms, okay? And you're going to allow few violations, like I said. You will allow a few violations using the soft vector classifier, where you're going to, spam email classified as not spam or vice versa. Okay, you can maybe email that's supposed to be a spam, you can classify that as not spam deliberately. And why are you doing that? You're doing that to build what I call a better generalizing classifier, because that we are, with the moment you allow misclassification, your model is going to be robust. Okay, we do that for robustness. Now, how does the model change? Please pay attention. Okay,
你
go ahead.
今天有网课是吗？
Go ahead. You want to ask a question? Hello, is there somebody say something? Did anybody say something? Okay. If you are not asking question, you are advised to mute. Okay. If you are not asking question, you are advised to mute. Okay. I want you to when we're considering what is the difference in the model, I'm going to take you back. You can see here for maxima margin classifier, there's no any error. Okay. But what you're going to see in the other one, you're actually going to see error included. Take a look at the soft one now. Oh my God. Can you see the error here? Okay, that very error is going to be called a slack variable. Okay, so which is actually going to tell us the extent of violations of due to misclassification. Okay, so like I said, I need you to pay attention to all of that. So you can see we still have the same optimization problem, except that we have incorporated error, okay, which we call the slack variable. Okay, the slack variable will allow observation to be in the wrong side of the margin or the wrong side of the upper plane. That's no problem. We are intentionally, incorporating that. Okay, but there's something I quickly want to mention. Please, I need you to pay attention. Okay. Can somebody confirm again, if you are still hearing me clearly? Is everyone still hearing me clearly? If you are in this class, I need you to confirm if you are hearing me clearly. Okay? I believe you are hearing me clearly. Now, what happened? So what happened? Okay, thank you for confirming that. Now, I said something here. What happened when error equal to 0? What do I call error the other time? Okay, what I actually call error is that error measure degree of violations of the margin. I'm going to say that again. Measure degree of violation of the margin. So when error equal to 0, okay, then the observation is correctly classified. I'm going to say that again. When error equal to 0, observation is correctly classified, even though it is outside or exactly on the correct margin. No violation of the margin or hyperplane. Okay, no violations. Okay, okay. I just wanted to take note of that. But what of in a situation where error is actually greater than 0? That is where we have some kind of violation. Okay, but let me tell you this: with error greater than 0, we're going to say it's correctly classified, but inside the margin. I'm going to say that again: correctly classified, but inside the margin. Okay, and the moment the error is close to 1, then the closer the observation to the hyperplane, when error is close to 1, the closer the observation to the hyperplane. Geometrically, I'm actually going to say the point lies within the margin in that situation. But you know what? Oh my God, what of in a situation where the error is greater than 1? Okay, this scenario is terrible. This particular scenario is terrible. In that situation, you're actually going to misclassify observation. And not only that, okay, it's going to be on the wrong side of the upper plane. Okay, it's going to be on the wrong side of the upper plane. I'm actually going to call them support vectors, but they violate both the margin and the classification boundary. They're actually going to, violate both the margin. Okay, like I said, they're going to violate both the margin and the classification boundary. Okay, I think that's all what I got for you today. But before I go, I'm actually going to say something. I've already graded and published the midterm 2, and I added extra credit of 5 point across board for that, even though the performance was not the one that I actually expected. Okay, you know, but what I observe in the class, those who come regularly to class, they actually do well. And those who do not come regularly to class are those ones that actually didn't perform on average to expectation if you come to my class. you listen attentively, and you also attend my review of practice questions, you should be good in my exam. So I have the booklet, and of course, the booklet will be distributed on Monday, for you to be able to see, what you get wrong, and of course, the solutions are already published. So, is there any question before I go today? I'm gonna return to in-person teaching on Monday. Make sure you all stay safe and have a lovely day. Bye for now, everyone.